Hi there, my name is Emmy and welcome to the second module of Day 5. I'll be talking to you about applications of derivatives. Please pause this presentation at any time when you need more time to think about something. There are many applications of derivatives. One of the applications of derivative is to solve optimization problems. These are problems where we try to find the optimal solution to a given situation. For example, a farmer might want to know just how much fertilizer to use to maximize the yield of a crop. Another example is where a manufacturer of 1,000-liter cylindrical steel rainwater tanks might want to know what the radius of the tank should be to minimize the amount of steel used. We will limit our problems to relatively simple examples of optimization. To find the optimal solution of the function y, we first find the values of x for which the derivative of y with respect to x is 0. In other words, we find the stationary points. Then we determine the nature of the stationary point either as a maximum, minimum, or neither. Recall from Day 4 that one of the two types of stationary point is a turning point. Now we need to determine which type of turning point it is, a maximum or minimum. Notice that for a maximum turning point, the sign of the gradient goes from positive to negative as we go left to right through the stationary point. Similarly, for a minimum turning point, the sign of the derivative goes from negative to positive as we go left to right through the stationary point. So suppose that f has a stationary point at x equals to a. If the derivative of f changes from negative to positive at a, then f has a local minimum at a. For example, if a baker sells bread for $X each, the profit gain is given by 30x minus x cubed. We want to find the price of the bread to give the maximum profit. Keep in mind that since x is the cost of the bread, it should be greater than or equal to 0. First, let us introduce a function p, which measures the profit of the baker in terms of x. We can find the stationary point by differentiating p, letting it equal to 0, and solve for x. And so we get x equals the square root of 10, which is about 3.16. Note that we disregard the other solution, x equals to minus square root of 10, since we know x cannot be negative due to the nature of the problem. We now confirm that whether we have a maximum when x equals the square root of 10. If x is less than square root of 10, say x equals to 3, then the derivative of p is more than 0. If x is greater than square root of 10, say x equals to 4, then the derivative of p is less than 0. Here the derivative changes from positive to negative, so p has a local maximum at $3.16. The corresponding maximum profit can be found by substituting 3.16 to the function p. So the maximum profit here is $63.25. Let's consider another example. A farmer wants to make a rectangular paddock. The farmer has 100 meters of fencing and wants to make a paddock that will enclose the greatest area. What dimension should the rectangle be? First of all, it is good to visualize what the problem is, so draw a rectangle representing this paddock. As a first step to solving this problem, define the variables needed. Let x be the length of the one side of the rectangle and y be the length of the other side. Let a represent the area of the rectangular paddock. You can label these variables in your diagram as we did in this previous slide. Then write down the function a in terms of x and y. Remember that our objective in this problem is to maximize a. In the next step, we can write any constraints for our variables. Here, we know the fencing has to be 100 meters, so the perimeter of the rectangle, given by 2x plus 2y, should be equal to 100. Rearranging the equation in the last step, we find that y is equal to 50 minus x. Then we can substitute this into a, so we have a equals to 50x minus x squared. Now the function a is in terms of one variable only. Differentiate a with respect to x, set the derivative to 0 and solve for x. We find that x equals to 25. Now we need to confirm whether this x will give us the maximum or minimum area. If x is less than 25, say x equals to 24, the derivative of a is positive. If x is greater than 25, say x equals to 26, the derivative of a is negative. As the derivative changes from positive to negative, a has a local maximum when x equals to 25. So let's go back to answering the question. Since x equals to 25, y, which is given by 50 minus x, is 25 also. So the farmer should make a square paddock with each side 25 meters long for the maximum area. Before we move on, the following points should be noted in this question. We have implicit bounds on the possible values of x. This bound is that x has to be between 0 and 50, including 0 and 50. Why do you think this is? What is y in terms of x? Does it make sense to have x greater than 50? When we have such bounds, we should also check the values of a at the endpoints of the interval. So for x equals to 0 and x equals to 50, we find that a equals to 0. And this is the minimum value of a. The steps we have taken to solve this problem can be summarized as follows. First step, draw a diagram, if appropriate, and define your variables. Next, write down the function to be maximized or minimized in terms of your variables. And find any relationship between your variables. Then we write one of the variables in the previous steps in terms of the other. In the next step, substitute the result into the function you are maximizing or minimizing. This means that the function you wish to optimize will be in terms of one variable only. Then we differentiate, set the derivative to 0, and solve. Make sure to check that the solution gives a maximum or a minimum. And then finally answer the question which was asked.